Hello, everyone, and welcome to our talk. Let's just do an audio check. Can you hear me?
Yeah.
Can you hear him?
Can you hear me? Awesome.
Good. So today we're going to present to you what is basically the result of a couple of years intense work on the web platform. The web platform has been broken for, well, since it was there, because it wasn't invented as an application release platform. It was intended initially as just content, linked content. Nowadays, everyone uses the web for other purposes, and so we thought that maybe it's time to make a change and make it behave as programmers expect. Little bit of introduction. I'm Roberto Clapis. I am a software engineer in security in Zurich, and my team and Michele's, which I'm going to introduce in a moment, works in creating a process for targeted problems that we find in the platform. So when we find that there is an API in the web that is always broken and everyone uses wrong, we assume that the problem is not the programmer, the problem is probably the API. So we try to provide simple ways to make it easy to use it securely. And I'm going to give the lead to Michele Spagnuolo, who is working with me in Zurich too.
Thanks, Rob. Hi, everyone. First of all, I'd like to know approximately how many of you know what is a cross-site scripting vulnerability, or XSS. OK, awesome. Cross-site request forgery? OK.
Sorry.
What is Spectre or Meltdown? OK. OK.
Pretty good.
Yeah, very good, very good. Tough audience. OK, so so in brief, cross-site scripting vulnerability is a web vulnerability that enables attackers to run malicious JavaScript in the user's browsing context. So the security boundary for the web is the so-called web origin. XSS is a violation of the so-called same origin policy, right? So basically, XSS vulnerabilities are traditionally split into two types, server-side and client-side.
Yeah, you can find all the kind of splittings, like you can find reflected, stored, everything else. It's just, for now, today, we're just going to do the basic split.
Yeah, so we are just simplifying it a bit and saying that there is reflected XSS, where basically the server reflects back a payload that an attacker sends. And we have DOM-based XSS, which is client-side. So it would work if you have an index.html file saved on your desktop. Okay, doesn't require a server, and it is because the DOM API is broken. I mean, it works.
Powerful.
It's powerful. It's broken.
It's
broken. It's not safe by default, as we like to say. So the traditional solution to XSS, and what we hear often is you need escaping.
Yeah, like manual escaping, like with pen and paper. OK.
So what does escaping mean?
So escaping, I would say that when you need to put a string in your page, you should consider where you put it. So if it is a CSS, you escape it as CSS. If it is a JSON, you escape it as a JSON. If it is a JavaScript, you escape it as a JavaScript. And then there is an inline event handler, nesting context,
math,
math, and then there is the template.
Yeah.
And then I think you can also have a template inside
you can have
JavaScript.
A template. Inside.
It's quite a bit.
Yeah, so it's very error-prone. You cannot do that manually, OK? Because there are different parsing contexts. And this is why manual escaping is not a solution. It's very hard to deploy, and it's very error-prone.
Yeah, and think about reviewing your application. You just see your code, and you see, oh, this is escaped. But you need to always keep in mind the context that the browser uses, even when you write the server-side code.
Yeah, and especially for DOM-based XSS, which are actually the most common types of XSS. The real problem is that unsafe DOM APIs exist, right? So, and it's not just inner HTML. So you might have read somewhere, inner HTML is dangerous. Yeah, but it's not just inner HTML, right? It's all of these, right? It's location open, it's a lot of attributes on HTML element, it's assign, it's insert adjacent HTML. So it's very, very hard. It's a hell. It's very, very hard to review all of them.
It actually took us quite a bit to put together this slide, and it's not even complete, because some colleagues of ours found even more.
So a better solution that does not ask the developers to actually, manually escape every sync is to use a templating system. So what is a templating system? A templating system is something that generates markup, so HTML, right? On the server side, usually, sometimes client side, depends which technology stack you're using. And for Java, Python, Golang, there are alternatives. Like for Java, you can use Google Closure template. Also
everyone has heard of it.
Yes.
Yeah, everyone uses it. I'm sure everyone uses a.
So this is a huge problem, right? Templating systems are not very known outside of big tech corporations, right? In Python, you can use with recent Django, you can kind of use their own templating system, but you have to avoid safe and a few other things you need to look for.
Yeah, basically it ends up being, in most templates, since they're very hard to use and very hard to write, you end up grepping for potentially dangerous APIs, which is not exactly scalable. So, yeah. Sometimes people, even with safe templates, tend to add a mistake to their application. And we don't want those mistakes to become exploitable vulnerabilities. Hence, we decide to drive a development of a new API.
Yeah, so some other languages like Go have a little bit better alternatives like HTML templates or even better safe HTML templates. But what we use internally at Google is the concept of safe types. So do not allow the developer to do string assignments to dangerous DOM APIs like in HTML, but actually force them to use safe types that have some security guarantees. This is why, together with others in the web platform and W3C, we are introducing the concept of trusted types to the web platform.
Yeah, I know it might seem weird if you're JavaScript developers and you think, whoa, types? It's fine. It's fine. You'll get used to it. I got used to it. It's fine.
Yeah, types won't bite you. So the idea is when you have a trusted type policy enforced, which right now uses actually piggybacks content security policy header, which we'll talk about later. The DOM asyncs actually reject strings, so you cannot longer do unsafe assignments like element inner HTML, something that introduces a DOM XSS, but you have to use a typed object. And this actually enables a lot of good things. It makes assignments explicit. It makes them reviewable. And basically, you have some guarantees that if your policy is safe, your whole application has some safety guarantees.
Yeah, basically, this restricts so much the amount of code that must be reviewed to check for vulnerabilities that is very hard to get it wrong. Moreover, this brings this concept of safe templates from the server side to the client side, because now it's not just about compiling your templates and checking the type system. Even if the template has a mistake, this is enforced at runtime in the browser.
So this is particularly useful for client-side apps, right?
Yeah. I mean, how many here use fat client application like Angular or React, like client-side frameworks that, so this kind of application is particularly sensitive to these vulnerabilities.
Yeah, trusted types support has been recently introduced in React, for example. And I think also Angular has some...
Angular will get it.
Ongoing, yeah. So there's a link here, and then there will be a QR code with a slide. So this is a specification, still a work in progress. It's being shipped in Chromium. I can't say the version, so we don't know it.
Yeah, it will get there.
Let's not, soon. Okay, so XSS is still a big issue. It's actually the top web vulnerability. We have a vulnerability reward program at Google. Mozilla has others. It's consistently the first vulnerability we receive reports of.
Fun fact, I was reading a book on web security recently, and there was one chapter on XSS that just said, XSS is easy to prevent, you just need to escape. So we are not going to talk about it.
Did you continue reading the book?
No.
Okay. Some XSS are very hard to prevent, actually, especially DOM-based XSS. And what we call defense in depth, which means some second layer of defense that actually comes to save you when the primary security mechanisms fail, is actually still very important. And I know that the community, and the security community especially, is very divided on especially the word mitigation. Mitigation is somehow an overloaded word. Like there is, mitigations are bad, mitigation just raise the bar, they do not solve the bugs. Right?
You just make it harder to exploit.
Yes. And here I like to, in this very text-heavy slide, I just like to say very quickly.
And by the way, I told him these slides have too much text in them.
Yes, and I love it.
That is a discussion that happened.
Yes. So there are good mitigations and less good mitigations. Good mitigations, we argue that the good mitigations are the ones that reduce the attack surface as side effects. So they have a hardening side effect. When you introduce CSP, you also actually do a lot of hardening steps just to introduce content security policy. You remove inline event handlers, which are unsafe. You refactor uses of eval, which you shouldn't have in the first place. It's actually very slow also nowadays, so don't use it. It gives you an incentive, especially nonce-based one, which we'll talk about later, to use contextual out-escaping templating systems, which is good. And how many of you have heard about content security policy in any way? CSP.
Oh,
okay. Someone.
Good.
Okay.
For a long time, CSP has been this complicated, hard to use, hard to deploy mechanism that didn't really even work very well.
It didn't work at all.
Exactly. It was the other kind of mitigation that we don't like, that just makes it slightly harder to exploit stuff. So someone, which includes Mickey, decided to change this a bit and revise the way it works to make it as simple as possible to deploy and provide actual mitigations.
So the idea behind traditional CSP was, we just want to execute our own scripts, not other people's scripts. So we just add a whitelist of domains from which we execute JavaScript from. We call it script SRC, and then we just add all the domains. So as Donald says here, sounds good, doesn't work. Basically, more than 95% of the policies are automatically bypassable.
Because people were literally adding all the sites, all the sources, all CDNs. So clearly, if you allow a CDN to execute JavaScript on your application, it's quite a bit of JavaScript there.
So I won't go into detail, but if you are interested, there are some links down there, it doesn't work. Okay, so don't use it. But what can we do?
Well, what we thought is that instead of blessing domains or origins, why don't we just bless scripts? But in a way that is easy to deploy, and in a way that an attacker cannot guess. So that changes every time the page is loaded, so they can't really predict the situation in which they have to exploit. Hence, nonces were created.
Yeah. And so we talk about what are CSP nonces in the next slide. But the important thing is we do have a lot of type of CSP, but we'll focus on the ones you can use. Because you are developers, I think, most of you, so you care about what works, not what we have gone through to make it kind of work. So if you're interested in more detail, there is an in-depth talk by Lucas Weichselbaum and myself, which explains what was our journey at Google modifying CSP and actually making it work. But the important thing is you have to use nonce-based CSP. So what is a CSP nonce? So a CSP nonce is very similar to a cross-site request forgery token. So it is...
which I will talk about in a bit.
Right. So it is a unique number. Okay. You usually put it in a base 64 encoded way that is unique per response. Okay. It goes into a HTTP header, response HTTP header, in the script SRC. So you do script SRC nonce random. Okay. Please do not put random. Right.
We have found these. Don't laugh. This is serious. We have found people deploying CSP with random with a 4 instead of the A. Don't.
So we presented CSP for the first time, I think, 3 years ago, and we put random with a 4. And we actually searched the web for that, and we found many, many websites that were actually sending our random with the 4. That was bad.
He literally downloaded half of the web out of the web on his workstation, just the headers.
And
fun story.
Anyway, okay, so you put that nonce in a script tag as a nonce attribute, and they have to match. So why does this protect? It protects because an attacker cannot see the header, the HTTP response header sent by the server, so it cannot inject a payload with the same exact nonce. If the nonce is not reused and it is random, basically this is an effective protection blessing one single script. So a script with a correct nonce will render and will run. Without, it will not. And here is an
basically,
example.
even if the attacker has full control of a little bit of content in the page, doesn't know the nonce, still protected.
Yeah, exactly. So the problem is we can nonce all the script we control, but it's very hard to nonce scripts that are dynamically loaded by scripts.
jQuery. Sorry.
And widgets like Facebook, Twitter,
all the things that just add stuff to the page.
And you usually block with your ad blocker. So these actually make nonce-only CSP very hard to deploy. So what we created is another keyword called strict dynamic that basically says only the parent script has to be nonced, and all the scripts that nonced script loads, they're automatically blessed for execution. This sounds like a compromise, but it's actually not so bad in terms of security. If you think about it, you explicitly blessed the parent script. So that script can do anything it wants. Okay?
Yeah, and also if there is an injection in the parent script, you're already executing JavaScript. So it doesn't really make sense to add your payload in another script tag. You're already there.
So very effective CSP and actually pretty easy to deploy is just doing this. Script src, the nonce, and strict dynamic. And then putting two other things, which I will not go into detail. Just trust us. Object source none disables disables plugins, and base URI none disables weird things. So
to be honest, if you do object source none, your application in Flash could stop working. But if that happens, it's still good.
Yeah. So the reason is plugins can sometimes bypass CSP. I mean, can bypass everything, so we should not use them. And base URI is because an attack that is called, it's basically redirecting relative scripts.
Do you really want to go there?
No, I don't want. Okay, so the refactoring steps are this. So you have inline event handlers, like the on-click there. You have to get rid of it. In a normal script tag, you add an event listener click. Okay, this is what you should do, and probably your JS framework does it already. Okay, so if you have on-click on error, it's bad. Don't use it. If you have a script tag, you have to nonce it. And if you're using eval, you have to use a better function. Are you using?
So you're just suggesting do not be evil.
Yes,
right?
don't be eval.
Yeah.
Yes.
Okay. Yeah,
so JSON parse, for example. Are you using eval for JSON? Use JSON parse. It's more secure and it's faster nowadays. There is no real reason to use eval if not for obfuscation and if you're running weird emulators. In that case, well, sorry. So it's a good trade-off between refactoring and cover syncs.
Yeah, keep in mind that refactoring to deploy CSP actually removes vulnerabilities.
Yeah.
You're not just doing it for CSP, you're doing it to improve the quality of your code, which also becomes better to maintain.
Yeah. So the only con is that some DOM XSS are still possible, especially injections in dynamic script creations. So this is narrowing down the attack surface by a lot, if you think about it. So we are not vulnerable. We're no longer vulnerable to JavaScript URIs, all these things that are actually usually what we see in real work.
Yes, I've seen a lot. I've tried, actually, I am deploying CSP on a lot of Google products, and this refactoring bit take quite a bit of time, but yeah, we find that kind of stuff everywhere.
Right, so I forgot about browser support. Strict Dynamic is supported by all good browsers. Better way is using nonce only. So just before, but without strict dynamic. Okay? So you don't have trust propagation. Yeah. This is supported by even more browsers. Even the other browsers.
Even the other browsers. Let's not get there.
Yeah.
We don't want to restart the browser war.
Yeah. So the only difference is that you have to actually add set attribute nonce for the scripts you dynamically create. Okay? This might be hard, or in some cases impossible if you don't control that part of the code. If you can, then you have the holy grail. All traditional XSS things are covered, and basically if you are in control of a JS, you're good.
Yeah, and I mean, this is doable. Seems hard, but I added this to the Chrome Web Store, for example, and it is a pretty complicated application. We added more content to the slide to allow you to check your CSP, work on it, and
yeah. Please do use the CSP evaluator. It's very, very nice. You just put a web page or you paste your CSP. It tells you in how many ways we can break it, and it's very cool.
Yeah, at this point, we were like, okay, we're confident that most XSSs are taken care of by templating system. We have CSP in case those fails. Well, now we have everything else. For example, cross-site request forgery. This is a form that could be in your application and that submits some data to your server. Your server is going to get a payload that just tells it the cookies, because the browser is always going to add the cookies for the destination, not for the source, the action, and the quantity. So in this case, your server has no way to determine if this comes from your site or another site that is just trying to exploit the fact that the user has a cookie for your service. To resolve this, usually we saw unique tokens that were added to the form in hidden fields. You have to use a framework to do that. You don't want to do that by hand because you have to plumb in a lot of things. You have to remember the checks. It's usually opt-in and not opt-out. And even if you use a framework, it might not get it right because the frameworks assumes that all GET requests, for example, are not going to change the state of your server, are not going to accept an action or submit a request. But this is not necessarily true. I mean, nothing really prevents you from reading a GET and then accessing the database or do different things. The framework just assumes that you respect the HTTP specification, which, of course, any one of us knows by heart. That said, we realized this doesn't really make sense. We can't expect everyone to do this. Even in Google, we saw a lot of vulnerability reports about CSRF because we weren't taking care of those correctly. So what we did was decide to change the behavior of cookies. Now when you set a cookie, you can specify flags. You can say, I want this cookie only if this action comes from my application, from my origin. And you can do it in two different ways. First one is, okay, if someone just navigates, so if someone just is going through a navigation and gets to my site, it's fine, still fine. I still want the cookie. This reduces the protection but makes your application actually usable and linkable. While instead, if you set it to strict, for example, if you're a bank, you don't want people to deep link to a bank transaction. This even blocks most of other attacks. This was not used. So we announced this, it's supported by every browser. We saw that basically no one was using this. So we decided to take the first step
and break the web.
And break the web. Yeah, so we decided to push this to Chrome and see who screams, basically. That said, there were other vulnerabilities that we didn't really fix because there are still side channels. If you're a developer, usually what you have in mind when you develop your application is your own application. You don't consider that other applications actually have access to what you do, because the web doesn't have strong boundaries. And so when someone visits an application in another tab of the browser that you don't have control of, they can infer some information about your own application by just abusing the fact that the browser is only one, shares the caches, shares many things, and shares the same hardware. Spectre is a vulnerability that we didn't expect to see exploited in the browser. We saw it. There are working exploits, and so we had to take care of this. For those who don't know, Spectre is based on the fact that your hardware tries to get so fast it predicts the future. And so when you have an if, any kind of if and kind of for in your code, and the first execution, your hardware does not know how to predict. So it decides to just execute in a slow way. But then if it collects information, it sees that one of the branches might not be often taken. So it says, OK, next time I get here, let's just go through the thing that is taken more often and ignore the other one. And then if I realize it was slow or wrong, I just roll back. Of course, the rollback is not perfect and sometimes can fail. So this branch prediction mechanism allows to observe the side effect of these choices. So this, I'll show you an exploit in 5 lines, can allow people to actually exfiltrate data that is in their process, even if they don't have access to it because of same origin policy or some other mitigations. This vulnerability is called Spectre because, and it has a branch.
Can you explain the logo?
Yeah. It's speculative execution, so spec, and the branch predictor is the vulnerable part, so that yeah, we have good humor. That said, this is an example. There is some secret value that you want to guess, you want to read. And what you do is that in 2 consecutive lines very close to each other, you read the value that you don't have access to, and then you use it to load some memory. If you execute this a lot of time with memory that you have access to, the branch predictor will run this code. And then the one time that the index that you control goes out of bound, it will still execute the branch, so you can observe the side effect of this choice and read what that value was. So if you have something like this, you can bring the destination resource in the memory of your process and read it with Spectre. This is, of course, not good, and we tried to create a heuristic to detect when that kind of stuff, for example, the first one, was not a script. You should not be able to obtain something as a script that is actually a JSON or an XML. And we come up with a very simple flowchart that we implemented in Chrome. This is intentionally unreadable. Not that the version with the fonts is actually readable. And
it was very evil.
Yeah.
To have it unreadable on the slides.
Yeah, I'm very evil. Yeah. Yes. So the
said it was a bad idea.
Boxes at the bottom are block and allow. I'll just tell you that. So we decided to implement this in Chrome. By default, it blocked some attacks, but doesn't prevent everything, because of course there are escape hatch and it was too complicated. So we decided, okay, let's just give people the choice. If they want to protect themselves from this kind of attacks, they just set cross-origin resource policy, and this will skip all that flowchart and just say, okay, block. If someone is trying to fetch this JSON cross-origin, I don't want them to use it. So you just set one header and you're done. But then we realized, what if they want to tune it? What if they want to have smart choices or like have a more complicated logic? This didn't scale. We can't just keep adding headers. I mean, we can keep adding headers, but as we saw with set cookie, people are not going to use it. So we decided to send to the server how a decision was made. When a resource is fetched, we just decide to send all the information to the server and let the server decide if it is the case to respond or not. And for example, this is a couple of headers that got added, and with just this information, you can see, okay, this is cross-site. There was no coarse pre-flight request. The browser just decided, okay, this is fine. I'm going to allow this. The server might not like it, and to create a policy to prevent this kind of attack is very easy. This is Go, which is not per se particularly short as a programming language, but as you see, this is the entire policy that you need to put on your server to protect from a lot of kind of attacks. And since we got here, we thought, okay, we block the resources. We give the means to block resources, but we weren't done. Because there are some attacks that don't need to load resources, they just need to open windows. So let's say that you have evil.com that opens a window to your application and then navigates it and checks what is now in cache. It can detect what happened, and by just using this information, it can leak some bits. So I'll give you an example. In Gmail, for example, there is a very smart search feature. And that feature allows you to filter through emails. And let's say that I put like a very long query that search for 4 digits numbers. Just half of them. So 5,000 items. And then I do the other half. And then depending on how much time it takes to load, I know if there are results or not. These could leak your credit card in under a minute from Gmail, from another origin. This was not particularly fun. We tried to mitigate it with CSRF token and abusing them, but bookmarks stopped working, other features stopped working, everything exploded and caught on fire, bad things. Don't do this. And even if when we were done adding this kind of mitigation, we realized there was another attack. Because when someone sent an email with a link, if people clicked on the link, the Open tab could navigate Gmail because there was a connection between the windows. They could just do window.opener.location and just move Gmail to a page that was identical, but except it was asking for credentials. This was nope. This was the biggest nope, and so we decided to change this thing. With this header, we just said, okay, this application is intended to be used alone. No cross-origin windows, no cross-origin links. Sever the link between windows when this header is set. And we were left with the first navigation. There was still a problem. and we decided that we could be good, but we weren't. And so we added one more feature, which is double keyed caches. Now we use not just their destination origin, but also the source origin to detect if something should be cached, something should respond from cache, and it's actually prevented some very nasty attacks. For example, in Twitter, there was the so-called silhouette attack. The way it works is that, let's say that you want to see who is a user. So you create 1,000 users, and each one of them blocks a different set of users. And then you just try, from that user, to visit all those profiles. Of course, a blocked profile will load the silhouette default icon, which goes in cache. So depending on how those pages respond, every time a profile loads, it gives you half and half and half of the search set. So in very few seconds, you can actually identify the exact user that is visiting your site. And to do a little bit of recap, most of the stuff we talked about was just in browser, so you shouldn't have any work to do. There is CSP, cross-origin opener policy, and cross-origin resource policy that you have to simply add, and a fetch metadata policy for which I linked to a repo, so you can just go there and write it in your own language. It's 5 lines. And thank you.